blockchains on voice-first applications. This is your voice-first podcast coming to you live from Pi, Thailand, where we continue to build voice-first applications on conversational AI. Today, exploring the blockchain technologies of Solidity and Ethereum blockchains. We're going to get started today with lesson 1, or I guess level 1, making the zombie factory. In lesson 1, you're going to build a zombie factory to build an army of zombies. Our factory will maintain a database of all zombies in our army. Our factory will have a function for creating new zombies. For each zombie, we'll have a random and unique appearance. In later lessons, we'll add more functionality like giving zombies the ability to attack humans or other zombies, but before we get there, let's have the basic functionality of creating new zombies. Okay, how zombie DNA works. The zombie's appearance will be based on a zombie DNA. It's a 16-digit integer. Just like real DNA, different parts of the number will map to different traits. The first 2 digits map to the zombie's head, second 2 digits to the zombie's eyes, and then keep going. Okay, so there's 8 different characteristics, and then each of those characteristics is 2 characters. We're keeping things simple. There are only 7 different types of heads, even though you could do 100 different combinations. Later we could add more head types if we want to increase the number of zombie variations. For example, the first 2 digits are 83. To map that to our zombie's head type, we do 83% 7 modulo 7 plus 1 equals 7. So this zombie would have the 7th head type. In the panel to the right, go ahead and move the head gene slider to the 7th head, Santa hat, to see what the 83rd trait would be. Put it to the test. Play with the sliders on the right of the page. Experiment to see how the different numerical values correspond to the different aspects of the zombie's appearance. Enough playing around. When you're ready to continue, hit next chapter and let's dive into learning Solidity. Okay, we got a bunch of eyes, got a bunch of shirts, got a bunch of skin colors, eye colors, and then clothing colors. Great. Oh, and there's a lot of variations in the clothes, color, genes. Next. Chapter 2, contracts. Absolute basics of Solidity code is encapsulated in contracts. A contract is the fundamental building block of Ethereum applications. All variables and functions belong to a contract, and this will be the starting point of all your projects. An empty contract named Hello World would look like this. Okay. Version pragma. All Solidity source code should start with a version pragma, a declaration of the version of Solidity compiler this code should use. The reason for this is to prevent issues with future compiler versions potentially introducing changes that would break your code. For the scope of this tutorial, we'll want to be able to compile our smart contracts with any compiler version of the range 0.5 to 0.6 exclusive. Looks like this. Putting it together, here's a bare bones of the contract, the first thing you'll ever write to start your first project. Okay, put it to the test. So we've got a pragma version and then what looks like a declaration of a contract. Let's create a base contract called Zombie Factory. In the box to the right, make it so our Solidity contract uses versions inclusive of 0.5.0 and exclusive of 0.6.0, which is exactly the same as what's defined up top. So we've already got pragma Solidity, so now we just need to add our numbers, which they've already defined here. No sense in me messing it up, so I'm just going to paste it with a semicolon to mark the end of the line. And then we want an empty contract called Zombie Factory. So now we'll just contract, I will copy the name so that I don't mess up the spelling. Zombie Factory. And that should be it. Let's check. Boo boo boo. Solidity cowers in front of your might. Lesson unlocked. Okay. Let's keep going. State variables and integers. Great job. Now that we've got a shell for a contract, let's learn about how Solidity deals with variables. State variables are permanent stored in a contract storage. This means they're written to the Ethereum blockchain. Think of them like writing to a database. Okay, so state variables are like writing to the database, and our database is the Ethereum blockchain. That makes sense. This will be stored permanently in the blockchain. Got it. In this example contract, we created a uint called an unsigned integer and set it equal to 100. Unsigned integers. A uint is a data type of an unsigned integer, meaning its value must be non-negative. I didn't know that. Unsigned means it can't be negative. There's also an int data type for signed integers. Note, in Solidity, uint is actually an alias for uint256, which is a 256-bit unsigned integer. You can declare units. Oh, might need to pause this to go plug in. You can declare units with a bit less bits, but in general you want to use uint, except in specific cases, which we'll talk about in later lessons. Our zombie DNA is going to be determined by a 16-bit number. Put it to the test, declare a unit called DNA digits, and set it to the value of 16. So we'll call it uint, boom, equals 16. Does that work? Solidity cowers in front of your minds. Lesson unlocked. Alright. 1 second to plug this in while we move to the next chapter. Next chapter, math operations. So we're going to try to get through all 15 of these real quick. Should only take us a couple days then to get through the entire CryptoZombies course. Math in Solidity is pretty straightforward. The following operations are the same as most programming languages. So we've got addition, subtraction. There we go. Multiplication, division, modulus, and remainder. Alright. Solidity also supports an exponential operator, i.e. x to the power of y. Oh, cool. X to the power of y. That's nice. Put it to the test. To make sure our zombie's DNA is only 16 characters, let's make another uint equal to 10 to the 16th. That way we can later use the modulus to shorten an integer to 16 digits. Create a uint called DNA modulus and set it equal to 10 to the power of DNA digits. Okay. We want it to be a uint DNA modulus equals 10 star star DNA digits. I think that's how we would do it. Check the answer. You've triumphed. Solidity cowers in front of your might. Lesson unlocked. Next chapter. Sometimes you need more complex data type. For this, Solidity provides structs, which looks like a class or an object. We got a person with an age and a name. Struct allows you to create more complicated data types that have multiple properties. Note that we've just introduced a new type of string. Strings are used for arbitrary length, UTF-8 data. For example, string greeting equals hello world. This seems pretty straightforward. Most people, I think, start with strings when they get into programming, so this feels pretty straightforward to just throw a string in without much explanation. So far, it seems like CryptoZombies is assuming a little bit of programming background, but also we're not doing very complex things, and I like that it's overlaying it on top of a game. Put it to the test. We want to create some zombies, and zombies will have multiple properties, so that is the perfect use case for a struct. Create a struct named zombie. Our zombie struct will have two properties, name, a string, and DNA. Okay. So inside of our contract, we will build these structs. We'll build a struct called zombie. Very simple. And then we want name, which is a string, so we'll make a string of name. And then we will have DNA, which is a uint. So now we'll have a uint of DNA. That should be good. Boop, boop. Lesson unlocked. Next chapter. Arrays. Okay, arrays. This is pretty common programming. When you want something, you can use an array. Two types of arrays, fixed arrays and dynamic arrays. Okay, so we can do a fixed array where it's declared with 2 elements, and then this one's declared with 5 elements, and then if we don't declare it with a number, then no fixed size, it can keep growing and shrinking. You can also create an array of structs using the previous chapter's person object. Okay, and then this would be an array of people of dynamic size. We can keep adding to it. Remember that state variables are stored permanently in the blockchain. So creating a dynamic array of structs like this can be useful for storing structured data in your contract, kind of like a database. So I'm curious, everything inside of the contract is a state variable? Like, are all of these state variables stored on the smart contract? Or is only the uints stored in the smart contract as state variables? Public arrays. You can declare an array as public, and Solidity will automatically create a getter method for it. The syntax looks like this. So we just add the word public after the array and before the name of the array, and then that makes it public, which I guess gets a getter method. Other contracts would then be able to read from them, but not write to this array. So this is a useful pattern for storing public data in your contract. Cool. Put it to the test. We're going to want to store an army of zombies in our app, and we're going to want to show off all our zombies to other apps, so we want it to be public. Let's create a public array of zombie structs and name it zombies. Okay, so let's make a zombie. Do we want it to be dynamic? We didn't say whether we want it to be dynamic or static, so I'll just make it dynamic. We do want it to be public. And then we want it to be called zombies. Let's see if that's right. Boom. Okay. Next chapter. Function declarations. Seems like it's just going through the base of all programming and just talking about it on smart contracts, which is great. Function declaration in Solidity looks something like this. You got the normal function keyword, the name of the function, and then the parameters, and it looks like you define the type in addition to the name. And then you can make it public if you want your function to be public. It takes two parameters, a string and a uint. For now, the body of the function is empty. Note that we're specifying the function visibility as public. We're also providing instructions about where the name variable should be stored in memory. Ah, the memory keyword. This is required for all reference types such as arrays, structs, mappings, and strings. What is a reference type, you ask? That is a good question. Well, there are two ways in which reference types brought up here. There are two ways in which you can pass an argument to a Solidity type. By value, which means that Solidity compiler creates a new copy of the parameter's value, passes it to your function. So not the actual value, but a copy of the parameter's value. This allows your function to modify the value without worrying about the value of the initial parameter that gets changed. By reference, which means that your function is called with a reference to the original variable. Thus, if your function changes the value of the original variable gets changed. Interesting. That's kind of cool. So we have the option of whether or not we want to pass in the actual value, and then that whatever, as it gets changed inside of our function, the outside value in memory also gets changed. Or if we just want to pass in the value, which copies the value but doesn't actually change the original variable. It's convention but not required to start function parameter variables with names, variable names with an underscore in order to differentiate them from global variables. We'll use that convention throughout our tutorial. Good to know. Okay, so underscores are common in Solidity at the start of a name to differentiate it from global variables. To use the function, we'd call it by saying vitalic 100. So this is actually going to change the value of vitalic because it's using it from memory. And then the 100 is going to be a value parameter, which means it's not actually going to change that 100. Put it to the test. In our app, we're going to need to create multiple zombies. Let's create a function for that. Create a public function named createZombies. It should take two parameters, a name and a DNA. Don't forget to pass the first argument by value by using a memory keyword. I'm wondering, okay, so it's required for all reference types such as arrays, structs, mappings, and strings. So does that mean anytime I want to use a string, I have to use it from memory? Like there's no way for me to just do value, I have to reference the string? If I always have to do it, it seems redundant for me to have to specify memory. However, we'll just keep moving through and see if that question's answered. Create a public function. All right. Function. We want to just copy the name so that I don't do any typos. Now we'll enter in all the parameters and then we'll make it a public function. That should be a solid function. And then we need two parameters. We want name, which is a string. So we want string from memory of name. And then we want DNA, which is a uint, and that's not a reference type, so we don't need the memory. So we just want uint. Uint DNA. Leave the body empty for now. We'll fill it in later. Ooh, I messed up. Function. and then we've got a string, memory, name, comma. Oh, something happened to my closing parenthesis. There we go. We are on chapter 8. This is the halfway point of our 15 chapter lesson. Working with structs and arrays. Let's create a new struct. Remember our person struct? Yep, that's an array of them. Now we're going to learn how to create a new persons and add them to our people array. Person Satoshi equals person 172 Satoshi. Add that person to the array. Okay, so this is initializing a new person struct, and then we're adding that person to the people array. Satoshi, if you're unaware, is Satoshi Nakamoto, who created Bitcoin. And Vitalik is a reference to Vitalik Buterin, who is the founder of Ethereum, one of the co-founders. We can also combine these together and do them in one line of code to keep things simple. Nice. I always like less lines of code, clean code. Note that array.push adds something to the end of the array, so elements are in the order we added them. So this will push 5 first, then 10, then 15, which then gives us an array of 5, 10, 15. Put it to the test. Let's make our createZombie function do something. Fill in the function body so it creates a new zombie and adds it to the zombie array. The name and DNA for the new zombie should come from the function arguments. Let's do it in one line of code to keep things clean. Alright, so we want to do it in one line, so let's just start by pushing to the array zombies.push, and then inside of that let's declare a new struct called zombie. Let's initialize that struct and then pass in the two parameters we need. We need a name and a DNA, so we'll go underscore name and then underscore DNA, and the underscores help us to remember that we're referencing these local variables instead of the global state variables. Well, not state variable, but struct variables. I think that looks good. Very straightforward. Chapter 9, Private and Public Functions. In Solidity, functions are public by default. This means anyone or any other contract can call your contract's function and execute its code. Obviously, this isn't always desirable and can make your contract vulnerable to attacks. Thus, it's good practice to mark your functions as private by default and then only make public the functions you want to expose to the world. Makes sense. Let's look at how to declare a private function. Just add the keyword private to the end, and it looks like we then use the underscore instead of just... I don't know why we add the underscore to this function. Maybe it explains it. This means only other functions within our contract will be able to call the function to add to the numbers array. As you can see, we use the keyword private after the function, and as well as with function parameters, it's convention to start private function names with an underscore. Okay, so I guess private functions we start with an underscore to signify that they're private. Public functions we don't have the underscore to signify that they're public. Put it to the test. Our contract's createZombie function is currently public by default. This means anyone could call it and create a new zombie in our contract. Let's make it private. Modify createZombie so it's a private function. Don't forget the naming convention. So we'll just make this private. And then we just need to add the underscore to signify the naming convention of private. Our total contract is less than 20 lines long, and we are on lesson 10. In this chapter, more on functions, we'll talk about return values and function modifiers. Return values. To return a value, the declaration looks like this. Return greeting. Great. Okay, so this one doesn't pass anything in. Public function, and then we have to say in the function declaration that it returns a string from memory. Okay. In Solidity, the function declaration contains the type of the return value, in this case string. Returns a string. Function modifiers. The above function doesn't actually... I still don't understand why we need the memory keyword. It seems like every time we use a string, we include memory. Is this just so that the programmer is aware that it's coming from memory? Or are there times when we don't need the memory parameter? The above function doesn't actually change state and solidity. It doesn't change the value or write anything. So in this case, we could declare it as a view function, meaning it's only viewing the data but not modifying it. Solidity also contains pure functions, which means you're not even accessing a data tape. Consider the following. Private pure, which means you're not even accessing any data in the app. So a pure function is all contained within the function. It doesn't access any data from the app. And then it returns a uint in this case. This function doesn't even read from the state of the app. Its return value depends only on its function parameters. So in this case, we would declare the function as pure. Note, it may be hard to remember when to mark functions as pure or view. Luckily, the Solidity compiler is good about issuing warnings to let you know when you should use one of these modifiers. Thank you to compilers for helping us coders not have to remember so much. Put it to the test. We're going to want a helper function to generate a random DNA number from a string. Create a private function called generateRandomDNA. It will take one parameter, a string, and return a uint. Don't forget to set the data location of the string parameter to memory. This function will view some of our contract's variables but not modify them, so mark it as view. The function body should be empty at this point. We'll fill it in later. Alright, let's start by creating a private function called generateRandomDNA. First thing we want is the function keyword, followed by the name of our function. Then we want parens to signify parameters. And then this is a view, so we'll say view, followed by private. And then our function body. Then we want a str string, so we'll say string memory underscore str. And then we want to return uint, and then we don't need to say memory because it's a uint. We want it view. I think I did view right. Let's see if we did it right. Public. Okay, so in this case they have, in their case they put the public versus private before they put view, and then they have returns last. I only did return and not the plural returns. Let's see if this is the right order. Okay, so I think I need to switch this around so that private comes before view. We've got the function keyword, then we have the function name, parentheses, string from memory of the name str, then we have a private view returns a uint. This looks better. There we go. We got it that time. Chapter 11. Keysack 256 and typecasting. Okay, I don't recognize this word. Typecasting seems like a term I was introduced to when I first learned JavaScript and TypeScript. We want a random number, generateRandomDNA function to return a semi-random uint. How can we accomplish this? Ethereum has a hash function called Keysack 256 built in. Okay, so it's a built-in Ethereum function, which is a version of SHA-3. A hash function basically maps an input into a random 256-bit hexadecimal number. A slight change in the input will cause a large change in the hash. Makes sense. So it's a cryptographic function that takes in a string and then outputs a hexadecimal number that's 256 bits. It's useful for many purposes in Ethereum, but for right now, we're just going to use it for a pseudo-random number generation. Also important, Keysack 256 expects a single parameter of type bytes. This means we have to pick any parameter, we have to pack any parameters before calling Keysack 256. Example. We get this out. I don't know what ABI is. And this one comes out from this. Okay. So we're encoding the packed string, and then we're generating a Keysack 256 hash function. As you can see, the return values are totally different despite only having a one character change in the input. Secure random number generation in blockchain is a very difficult problem. Our method here is insecure, but since security isn't top priority for our zombie DNA, it will be good enough for our purposes. Typecasting. Sometimes you need to convert between data types. Take the following example. Okay, so we want to generate a uint 8 by multiplying a and b, but because one's a uint and one's a uint 8, different types. So if we want to get a uint 8 out, we can cast our, I believe this is a 32-bit uint, we can cast it with uint 8 and then it'll work. In the above, a times b returns a uint, but we were trying to store it as a uint 8, which could cause potential problems. By casting it as a uint 8, it works and the compiler now will not throw an error. We're now getting into the weeds of compilers and casting. Cool. Let's fill in the body of our generate random DNA function. Here's what it should do. 1. The first line of code should take a keysack256 hash of abi.encode-packed string to generate a pseudo-random hexadecimal, typecast it as an int, finally store the result in a uint called rand. 2. We want our DNA only to be 16 digits long. Remember our DNA modulus? So the second line of code should return the above value modulus DNA modulus. Okay, interesting. First line of code should take a keysack256 hash. Okay, so now we want to go keysack256 hash of this packed string to generate a pseudo-random hexadecimal, finally store the result in a uint called rand. Uint called rand equals that. We want our DNA to only be 16 digits long, so the second line of code should return rand modulus DNA modulus, and this should reference our DNA modulus above. Think I'm doing it right? Let's check. Nope, did something wrong. Keysack256. Did I spell it wrong? And we've got abi.encode-packed, and then we've got the string, and then we return typecast it as a uint. Okay. So we just cast it. We just put a cast around it for uint. Boom. Next chapter 12. Putting it together. Great. We're getting to the wrapping up of this chapter. 13 or 15 is how long this is. We're on 12. We've got 4 left. Close to being done. Let's create a public function that ties everything together. We're going to create a public function that takes an input, the zombie's name, and uses the name to create a zombie with random DNA. Put it to the test. Create a public function called createRandomZombie. It'll take one parameter, a string. This function public just as you declared, the other one private. The first line of the function should run the generateRandomDNA function and store it as a uint named randomDNA. The second line should run the createZombie function and pass in name and DNA. Solution should be 4 lines of code, including the closing of the function. Okay, where does it want us to start? So we want to first start using the function keyword, followed by the name of our function, in this case, createRandomZombie. Now we want parentheses for our parameters, followed by the status, which is public in this case. Are we returning anything? Doesn't look like we're returning anything, so then we just have our function. We got 2 lines of code so far. This should be 4 lines. First line of code should run the generateRandomDNA underscore generateRandomDNA, and for that function we need a string. Oh yeah, I didn't get the parameters. So in this case we want a string from memory called underscore name, and that is it. So now we will generate random DNA using underscore name and store it as a uint because we're casting this as a uint, the return value. A uint called rand DNA equals, boom. Next line, we should run the create zombie function and pass in name and rand DNA. Now we just need to go create zombie. Create zombie needs a name, which is underscore name, and then it also needs a uint of data, which we just got from rand DNA. That looks like a good function to me. We don't need to assign this value to anything because create zombie does not return anything. So right now it looks like we just created a public function called create random zombie, so anybody can access this on the Ethereum blockchain and can create a random zombie by passing in the name of the zombie that they want to create. We then generate the random DNA for that zombie and create the zombie and push it to our array of zombies. And it looks like zombies is a state variable, so it's actually stored on the blockchain as a database. I believe that is how it is, because if it wasn't a state variable we would have the underscore, but because it is a state variable it does not have the underscore, which means that every time we push we are actually writing to the blockchain. I believe. This is my understanding of playing CryptoZombies so far. Our contract in total has 29 lines of code with 3 functions, 1 struct, an array, and then 2 uints. Let's check. Our contract is almost finished. Now let's add an event. Events are a way for your contract to communicate that something happened on the blockchain to your front-end app, which can be listening for certain events and take action when they happen. Declare an event, integer added, function add public returns, and then we emit an event inside of a function call. Okay. Your app front end code could then listen for the event. A JavaScript implementation would look something like this. Your contract.integers added function error results. Do something with the result. Let's put it to the test. We want to create an event to let our front end know every time a new zombie was created so the app can display it. Declare an event called new zombie. It should pass zombie ID, a uint, name, a string, and DNA, which is also a uint. Modify the create zombie function to fire the new zombie event for after adding a new zombie to our zombies array. Number 3, you're going to need the zombie's id.array.push returns a uint of new length of the array, and since the first item in the array has index 0, array.push -1 will be the index of the zombie we just added. Store the result of zombie.push -1 in a uint called id. So you can use this as the new zombie event in the next line. So id is just going to be the index in the array. Declare an event. First thing, let's declare an event up here. So let's call it event, and then we want to call it new zombie. This is an event that gets fired anytime there's a new zombie. And pass in a uint of zombie ID. Then we want a string from memory of name, and then we want a uint of DNA. Okay. Declare an event. I think we did that. Modify the create zombie function. Boom. We'll modify the create zombie function to fire the new zombie event after adding the new zombie. So we want to fire it by saying emit new zombie, and then we should pass in a zombie ID. So we want to do this part now. We want to store the result of zombie.push -1 in a uint called ID. So we'll have a uint called ID which equals zombie.push -1. Because since the first item has index 0, will be the index of the zombie we just added. So if we have an empty array and then we push one item, I guess it's going to return, oh, it returns a length of the new array. Okay, so if we push one item, we want it to return 0, but the length is going to return 1, so we subtract 1. I don't know that we need this parenthesis. Okay, so now we've got an ID. So now inside of new zombie, we need the zombie ID, which is ID. Then we need the memory of name, which is underscore name. And then we want the DNA, which is underscore DNA. And I think that should work. Let's see. Okay. Did something wrong with declaring the event. Uint. Maybe we don't need the memory? Okay, now I don't understand what memory's doing. It does seem like sometimes we don't need memory, but I have no idea when or why. We'll just keep moving. Web3.js. Our Solidity contract is complete. Now we need to write a JavaScript front end that interacts. Oh, this is cool. Ethereum has a JavaScript library called Web3.js. Never heard of this. Web3.js. Ethereum JavaScript API. That's great. Okay, good to know. We need to write a JavaScript front end that interacts with the contract. Ethereum has a JavaScript library. In later lessons, we'll go in depth how to deploy a contract and set up Web3.js, but for now, just take a look at a sample code for how Web3.js could interact with our deployed contract. Don't worry if this doesn't all make sense yet. Here's how we would access our contract. Variable ABI generated by the compiler. Zombie factory contract. We then look up the Ethereum contract. Contract address. Our contract address on Ethereum after deploying. Zombie factory contract dot at contract address. So we get the contract from our contract address from the Ethereum blockchain. Zombie factory has access to our contract's public functions and events. Great. Some sort of event listener to take the text input. So we've got a button, we click on it, then we get the value of a field called name input. We get the value of it, and then we create a random zombie with the name. So that will call our contracts, create random zombie with the name, and then we want to listen to for the new zombie event. So this triggers our event, or triggers our function, and then inside of that function, it emits the event, which I guess our page will then be able to receive right here. The event, factory new zombie, it's a new zombie event from our zombie factory contract. We get the results. If there's an error, return. Otherwise, generate zombie, which looks like it's going to generate the zombie on the front end. Take the zombie DNA and update our image. Function, zombie, ID DNA, let DNA string, pad DNA with leading zeros if it's less than 16 characters. If it's less than 16, we then pad it with zeros. Zombie details, first 2 digits make up the head. We have 7 possible heads. So %7 to get numbers 0 through 6. Then we add 1 to make it 1 to 7. Then we have 7. Image files named head1, head7. We load based on this number. Okay, so we're loading resources. All of these resources are stored in our front end code. The only thing that's stored on the smart contract is the creation of the zombies and the emitting of the event. It seems like some things get stored on blockchains and other things do not get stored on blockchains, depending on what we want in the contract. Head choice, we then get the DNA substring of the first 2 characters, modulo 7, modulo 11, modulo 6. I'm not sure what, oh, there's 11. Okay, so we modulo it by however many variations we have. We have 6 variations of shirts, we have 7 variations of heads, 11 variations of eyes, 6 variations of shirts, and then we keep going down the list of skin color, eye color, clothes color, zombie name, zombie description, boom, zombie details. What our JavaScript then does is it takes the values generated in zombie details above, and it'll use some browser-based JavaScript magic. They're using Vue. We typically use React to swap out the images and apply CSS filters. You'll get all the code for this lesson in later lessons. Go ahead, type in your name, and see what kind of zombie you get. So this one just looks like we're just playing around in the box. Voice first AI. Cool, so it just takes that string, it encrypts it in a hash, and then generates a zombie. That's really cool. I think we've completed lesson 1. You've completed level 1, you're officially one step closer. Here's a permalink of your zombie to share with your friends. Oh, that's cool. I'll tweet it out. That's so funny. I'm just gonna delete all these leading, trailing underscores, and let's see if it still works. Nice. That's cool. Okay, so now anyone that's on our Twitter, if you follow us at Voice First AI, you can see the CryptoZombie we just made. Looks like we finished. So what's the next lesson? You can find the source code at this GitHub repo. I don't care to sign in, so let's just go back. We just finished making a zombie factory. How do I go proceed to the next lesson? We did zombie factory. Next is zombies attack their victims. Cool. We've got another 5 lessons after this. And then there's a couple other modules. So we've got a while where we can be playing with this. If you have any questions, please let me know. I'm an intro to blockchain development, especially on, well, Solidity is the only thing I've learned. Overall, this seems like a good game. This reminds me of how I learned GitHub, which was GitHub Learn. And then you've got this nice learning Git branching.js. This is how I learned Git, was through playing games. I think playing games is a really good way to learn, especially code. And I learned a lot of code from Free Code Camp, which has lots of interactive lessons very similar to what this CryptoZombies was just doing. I recommend, if you need to learn more about Git, learn gitbranching.js.org. And if you want to learn more about coding, go to freecodecamp.com. And specifically, if you want to learn about blockchain, go on to CryptoZombies. This is really cool. If you have any questions, tweet at us, post on our Instagram, send us a message, listen to our podcast, and send us a voice message. All of those you can find us at Voice First AI. And if you want to help us additionally, right now we are heavily promoting our Alexa for Musicians product. So right now we are looking for musicians that want to put their voice on Alexa, and we're trying to figure out how to expand this platform with more blockchain-based technology. So if you want to earn money by putting your music on Alexa, or if you just want to message us about any of our other products, reach out to us at Voice First AI. And thanks everyone for tuning in. Remember to continue to find your voice.